In this video, we'll discuss similarity. Similarity of two objects occurs when the corresponding angles are congruent and the corresponding side measures are proportional. Now, what this means is that we're going to create a scale factor for those sides, which is going to be that ratio of the corresponding sides, to show that every side is proportional. One thing to also pay attention to is that while we're talking about similarity, all congruent objects are also similar. It's just that scale factor they have is 1 to 1. So here's an example of similarity. If I look at this, I could say that the left shape is twice the size of the right shape. This means that if I looked at all the angles, the corresponding angles here are all congruent, and then the sides would have a 2 to 1 ratio of the lengths, so that the ones on the left side would be twice the length of the ones on the right side. Now, if I looked at this shape, I would say this is not similar because I've lost that proportional ratio for my sides here. So you can see this bottom left and this diagonal are not proportional to what would be the diagonal in the bottom left of this shape or this shape. So how do we go about finding lengths of similar objects? Well, it's using that aspect of being proportional. So say I have these two faces here. I decide I want to blow up this funny face I've made and print it. My original down here would be the 8 by 12 inches. And I want to make it 4 times that size. So my scale factor would have to be a 4 to 1 ratio. So if I think about what that means, it means that every measurement on my left-hand side face is going to be 4 times that of the measurement for each of the lengths of my original. So if I think about this being 8 inches, then this would have to be 32 inches because 8 times 4. And if I think about the height was 12 inches, 12 times 4 is 48 inches. And if I look, those ratios are the same, 4 to 1 and 4 to 1. Now, within triangles, we have 3 different ways we can tell if two triangles are similar. The first being side, side, side. Now, in side, side, all corresponding sides had to be congruent. In side, side similarity, they have to have the same proportion. So if I look at my two triangles here, if I look at the corresponding sides, I have AB is 12 over DE 4. That's a 3 to 1 ratio. If I look at AC to DF, that's a 3 to 1 ratio. And if I look at BC to EF, that's a 3 to 1 ratio. So by side, side similarity, I can say that triangle ABC is similar to triangle DEF. Now we have side angle side congruence. We also have side angle side similarity. Same idea. The sides have to be proportional. The included angle has to be congruent. So if I look at this, I could say that KJ over HJ is a 1 to 2 ratio. LJ to JI is a 1 to 2 ratio. So I got my two proportional sides. And if I look here, what I have is that HJI and LJK have to be congruent because they're vertical angles. So I have two sides proportional, the included angles congruent. So by side angle side, I could say that KJL is similar to HJI. And the third method we use is called the angle-angle. Also, we call it sometimes the AAA, but you can get away with just 2 because if you know 2, you automatically know the third angle. So if we know that 2 angles that are corresponding are congruent, then the third one must also. Therefore, the triangles are similar. So if I look at this picture here, because I have these 2 parallel lines, I know that RMN, our angle here, and QMP are congruent because they're corresponding angles of parallel lines. It's that parallel line that's so important here. And here the NQP and MRQ are also congruent because of the parallel lines. However, we could have also used the fact instead of just having angle P, because NPQ and MPR, that's a reflexive angle. It's still angle P. So by AA, we know that triangle PNQ is similar to PMR. So where do we use this? So here's an example of how we can use similar triangles. Ben is 6 feet tall. He wants to find the height of a tree his parents planted when he was born. When he stands straight, he's casting a 4-foot shadow. He measures the shadow of the tree and finds it's 12 feet, so how tall is the tree? So here's my image. I got the sun shining, got my tree and my shadows. I can measure what I know. I know that this is 4 feet. I know Ben's 6 feet. I know the tree shadow is 12 feet. And I want to know the height. But what happens here, if you think about how is it that we're forming shadows, it's the sun shining down on Ben and on the tree at the same time, so that you get this imaginary third side of triangles. And when we think about it, that angle of the sun creating down to the shadow is going to be the same for both of these triangles, and you have the fact they're standing straight up, so if he's creating that same angle there to create the right angle. So we have angle similarity. We can use that to find the missing side. So it's just a proportional relationship where we know that the corresponding sides, 4 to 12, should equal whatever 6 to the height of the tree should be. I cross multiply and then I divide by 4 and I get that it's 18 feet. So the tree is now 18 feet tall. Another concept that comes with similar triangles is the idea of dealing with geometric mean. Now first, what is the geometric mean? If we have a geometric sequence of 3 numbers, so that means you multiply by the same factor or by the same scale each time, so like 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. That's a geometric mean. That's a geometric sequence. We can find the geometric mean, which is a number in between 2 numbers in that sequence, by using a proportion of A over B equals B over C. So we're finding a middle value in between 2 values. So say I wanted to find the geometric mean of 4 and 9. So what I'm looking at is the idea that 4 times some number gives me what's in the middle, our geometric mean, and that times that number will give us 9. So you can use our proportion. We don't know the middle number, so 4 over x equals x over 9. That's x squared equals 36, so x equals 6. Now let's put it back and see what that means. So 4 6 equals 6 ninths, which is 2/3. So they are equivalent fractions. But also, if we think about it in the idea of the geometric sequence, 4 times 1 1/2 gives me 6. 6 times 1 1/2 gives me 9. So I'm using that same scale each time to get to the next term. So I am following the geometric sequence. Now this happens to happen in right triangles, where if we create the altitude from the right angle, so the altitude is forming a perpendicular side with one of the sides, and so we're coming out of the right angle here, and here's our showing us that we're being perpendicular. We get a whole bunch of different ratios that are based on the geometric mean. The most common one uses that the length of CB over the altitude is going to equal the altitude over CD. It's one of the most common relationships. So let's see what that would be. So if I knew that if I want to find the entire length of segment DB, if I know the length of CB is 6 and the length of AC is 18, well, I can use this relationship. So 6, and I want to find CD. So we know that length is all that together. So 6 over 18 is equal to 18 over x. I cross multiply, divide by 6, and get to 54. So that means that CD is 54, which means here this is 54. So to find the length of DB, I can use the segment addition postulate. 54 plus 6 gives me 60. So I know the entire length of DB is 60. Now, why is this the case? So let's see what happens and why this relates to similar triangles. So if I can realize there are 3 different triangles in this image. I've got this triangle here on the left-hand side, ABD. I have this small right triangle here. I know this is the right triangle because if this is 90 degrees, CBD has to be 90 degrees. But then I also have to recognize I have the large right triangle where all of this started. Now, if I start doing comparisons, I see that I have the right angle in all three of them, but I don't have matching angles here, so I can't say anything yet about these two triangles. But if I compare ABD or BAD to DAC, I have angle A corresponding, and I've got the right angle, so that's angle tells me that this triangle BAD is similar to triangle DAC. Now let's look at the smaller triangle and my largest triangle. I have the right angles corresponding, and I both have angle C that's corresponding. So again, angle similarity tells me that BDC is similar to DAC. Now these two triangles are similar to the same triangle. That means these two have to be similar as well, since they're both similar to triangle DAC. So in this case, all three triangles are similar to one another, and because of that, we can say that the sides have a proportional relationship, and the way it lines up in our triangle creates these special geometric mean setups that can be very useful in finding missing pieces.